everyone, welcome to IFAS. I have a very special announcement for all of you. As you can see here in this particular slide, that we are starting a very special batch for the first time. IFAS is launching an English only batch. Okay, all the lectures in this batch for CSIR Net Chemical Sciences will be delivered in English only. All right. So as you can see, this batch is starting on the 14th of June 2021. So make sure that you call IFAS as early as possible to get all the information that you want about this particular batch. All right. So you know what our phone number is. Our phone number is given below here. All right. 917-2266-888. Call us on this number so that you get sufficient information of all the information that you need on this batch. Okay. So in this particular session, in this particular video, we are going to talk about what galvanic cells are from electrochemistry. Okay. So galvanic cells, as you know, they are cells that convert. Uh, they are devices that convert chemical energy to electrical energy. All right, and we are going to study the functioning of such. All right, so chemical energy to electrical energy is what we are going to study. All right, so let's see. Let's have a look at what we are going to discuss in this particular class. The first thing that we will discuss is something called as the Daniell cell. Okay, there is a very specific kind of cell, galvanic cell, which is called as the Daniell cell. And this Daniell cell, how does it generate electrical current or a potential difference, is what we are going to study in this particular class. After that, we are going to have a look at the energy that drives this kind of generation. Okay, what is called as the electrical energy, and how this energy is derived from the Gibbs free energy change during the cell reaction. Okay, so let's study galvanic cells. All right, now these galvanic cells, as I said, they convert chemical energy to electrical energy, which automatically means that there is a chemical reaction that is happening somewhere in our device. Okay, so you know what a normal 1.5 volt battery is. You have used such kinds of batteries multiple times throughout your life. We are going to see one such kind of a battery, which is called as the Daniell cell. But I'll explain a general form of the general device that actually generates an electric current and what is its mechanism. All right, so let's have a look. Let's assume that we have a solution. All right, so let's assume that let's say this is the zinc sulfate solution. I'll just mark the solution here. Okay, this particular solution that you see in faint green, that is, let's say, a zinc sulfate solution. All right, so typically what we can write here, let's assume that this is zinc sulfate. Okay, ZnSO4, right? And this rod is a zinc rod. Okay, this is a zinc rod. Okay, now when a zinc rod is dipped in zinc sulfate solution, what happens is zinc ions or zinc atoms have a tendency to convert into zinc ions. You know what the zinc atoms start feeling is that they are confined to the zinc rod. They want to be free, they want to roam around in the solution. So what they do is they try to become like the zinc ions that are there in the zinc sulfate solution, that is the Zn2 plus ions in the zinc sulfate solution. So what they try to do is they try to give away their electrons. Okay, when zinc atoms give away their electrons, what you will get are zinc ions. All right, so the kind of reaction that is happening here is zinc atoms, they lose electrons to get Zn2 plus and 2 electrons. Okay, now once this zinc atom loses its electrons, what will happen? These electrons naturally will naturally end up on the electrode. Okay, and it's a metal electrode, so it conducts electricity. So an electron that has been generated here somewhere will travel right to the end of the conductor. All right, and the zinc sulfate ions, the Zn2 plus ions that were generated, that will end up being here. Okay, so now what you can see here, is no more a zinc atom. What it has converted into is zinc 2 plus ions. Okay. Now, what will happen is the same thing can be done in a very completely different solution. Okay. Now, this time what we are doing is we are taking a copper sulfate solution. We are taking a copper sulfate solution and we are having a copper rod here. Okay, we have a copper rod here. Okay. Now, copper atoms have a completely opposite tendency as compared to zinc. Okay. What zinc likes is zinc likes to keep behind its baggage. It likes to keep behind all the electrons that it has on the electrode, and it likes to roam freely in the solution. On the other hand, what copper likes is copper ions. They want stability. Okay, copper ions, they want stability. They want to be in the same place. They want to know that their life is settled, their life is stable. So what we will do is the free copper ions that are there in the solution. Okay, you can see there are a few. There is one copper ion that I have shown here. This copper ion is free in the solution, but it doesn't want to be free. It is bored of traveling the world in the solution. What it wants to do is now what it wants to do is settle down. All right. So what it will try to do is it wants to go to the electrode here. Okay, because on the electrode all the copper atoms are very happy. Copper atoms are stable. Copper atoms are settled. All right. So what this copper ion is now trying to do is it is trying to go to the electrode and sit there stable, quiet, and settle down. All right. But when it goes to the electrode, there is nothing there to convert the copper ion into a copper atom because the copper ion still has charge. All right. It needs to neutralize that charge. So when a copper ion is trying to settle into the copper on the copper rod, it needs a house, it needs furniture, it needs a lot of things to settle down. That is electrons settle down. All right. So what will happen is what we are going to do is this copper atom, this copper ion, the positive ion of copper has now gone and applied to the copper rod of his. Okay. And it has applied for a house. Now for the house to be available, the house is currently here. The electron is currently here. This electron needs to be transported to the copper rod so that this copper ion, which is shortlisted for a house for an electron, it will gain the electron. What we will do is we are going to provide a highway for this house to travel from here to here, for this electron to travel from here to here. Okay, so what we are providing is a wire. Okay, this is an electrical wire, this is a metal wire. It has nothing to do with copper or zinc metal. It can be any metal. Typically these tend to be silver wires or platinum wires or even copper wires because they have very high conductivity. Okay, so we have provided some sort of a wire here so that the electron can now travel, and this copper ion which wants the electron to settle down can get the electron. Okay, so once the wire has been put in place, the electron will now travel and the copper ion will combine with the electron. Okay, so I'll show this to you again. Once the copper wire has been put in place, the electron will slowly travel to the copper rod, combine with the copper ion, and the copper ion is now settled. Okay, so in all of this process, see what has happened. There were zinc ions on the there were zinc atoms on the zinc rod. They like to be free, they like to travel the world. So what they will do is they'll keep behind their electrons. Those electrons will later be utilized by copper ions. All right, and there will be an extra positive ion in the zinc sulfate solution because the zinc atom has converted to zinc 2 plus. Okay, so there is extra positive charge on the left hand side this time. What has happened on the right hand side? There was a positive charge here, and that positive charge accepted a negative charge from the zinc electrode, which is why this is overall negative. Earlier there was one positive ion here, that positive ion has gone, so overall charge has become negative. All right, now what we want is to neutralize these charges because we cannot have charged solutions. Okay, everything tries to remain, tries to convert into a charge neutral environment. Okay, so what we are going to do is we are going to provide another bridge. Okay, we are going to provide another bridge for charges to flow in the direction they are necessary. Okay, so on the left hand side there is an extra positive charge. So what we are going to provide is, this bridge is going to provide an extra negative charge. Okay, and here there used to be a positive charge which has gone. It needs an extra positive charge, so we will provide an extra positive. Okay, so this is the entire way in which a galvanic cell functions. Now, what has happened is, because electrons were exchanged between the rod and the solution, and so on and so forth, or even the bridge that we provided, that also ended up exchanging charges with the solutions. Because of that, what we can say is there was a flow of charges. And when there is a flow of charges, we say that a current is flowing through the circuit. Okay, and if a current is flowing, it means that a potential difference was generated. This potential difference is called as the cell potential. Okay, this potential difference is called as the cell potential. All right, we'll talk about the cell potential a little more in detail later on, but right now let's focus on the galvanic cell. All right, so the components of the galvanic cell, now we'll name them. The one on the left hand side, anode, where the atoms like to travel the world. The atoms try to convert to ions and become free and travel the world. That part is called as the anode. That part is called as the anode. Okay, then the part which imports electrons from the anode is called as the cathode. All right, and the bridge that ensures that charge neutrality has been maintained, the bridge that ensures that the charge neutrality has been maintained, that is called as the salt bridge. All right, so let's see how all this entire system is now functioning. Okay, zinc leaves electrons, copper goes and waits for the electron, combines with it, and the salt bridge neutralizes, and the same process repeats over and over again, and charges are released by the salt bridge to ensure charge neutrality. So if you notice, at the beginning, at the beginning there is one positive charge here, all right, and rather there should have been two positive charges, because you will see that one of the positive charges has gone here and there was no charge here. But see what happens at the end. You will still see that on the left hand side you have two positive and two negative charges, all right, which means the left hand side is still neutral, and on the right hand side you have two positive charges, just like earlier, though these are different ions. These are not necessarily copper ions, these are ions that the salt bridge can provide. Typically they are K plus ions, all right. So these are again, they ensure the same number of charges on both sides. Okay, essentially charge neutrality on both sides. Okay, so this is what is a galvanic cell, and this is how a galvanic cell functions. All right, now let's try to solve a question based on this concept that has already appeared in the CSIR net exam. Okay, so this question came up in the CSIR net December 2018 exam, right? So the correct statement among the following is, okay, we have to figure out which of the given statements is the correct statement. Salt bridge is required for the mixing of solutions in two half cells. It's not required for the mixing. What we saw is salt bridge ensures charge neutrality. Mixing is not correct, which is why we can eliminate the first option. All right, let's look at the second option. Salt bridge allows current to flow between half cells without mixing the solutions. Without mixing the solutions. Yes, absolutely correct. That is what we had tried to ensure, because if the solutions have mixed, then we don't have any control over which ions are flowing where. What will happen is, if the solutions are mixed, when zinc leaves behind the electrons, they will immediately be taken up by copper itself, copper from the solution itself. It doesn't have to pass through the external circuit, and the overall mechanism is disturbed. So we don't want the solutions to mix, which is why we are using a salt bridge here. So the second option is the correct answer. Look at the third one. Salt bridge enhances the rate of the reaction. Does it increase the rate of the reaction? No. The reaction happens at the same rate. Only thing is, the salt bridge ensures that the reaction completes. Because if charge neutrality is not there, then the reaction won't complete. Okay, you won't have a circular flow of charge, which is necessary for a current to flow. Okay, so which is why the third option is also incorrect. Look at the fourth one. Salt bridge consists of a non-electrolyte in a gel. So if you have a non-electrolyte, it cannot provide charges. Okay, non-electrolytes cannot provide charges, right? So what that means is you have to have an electrolyte, because an electrolyte is the only kind of solute that can dissolve in a dissolve in a solvent and dissociate to ions, which have to flow into the respective solutions to gain charge neutrality. Okay, so which is why the second option here, the correct answer, salt bridge allows current to flow without the solutions mixing, right? Okay, let's look at the next part that we have to study. So this was all about galvanic cells. All right. Now, galvanic cells are based on the principle of oxidation and reduction. Okay. So what kind of chemical reaction happened in the galvanic cell? The reaction that happened was electrons left behind and electrons accepted. Zinc atoms uh, donated electrons to the zinc rod. They gave away electrons. Copper ions, they accepted electron. All right. So for that, for these two kinds of reactions, we have very specific names which you already know. They are called as oxidation and reduction. Okay, they are called as oxidation and reduction reactions. Now, what is oxidation? Oxidation is loss of electrons, whereas reduction is gain of electrons. Okay, so when I say that zinc lost electrons, okay, what happened here was oxidation, whereas what copper did was the electrons that zinc had given out, those two electrons this copper ion accepted, had converted to the copper atom. Okay, so what happened on the copper rod is gain of electrons, which is why we write reduction is gain. Now there is a very easy way to remember this, which is oil rig. Okay, this is a nice trick to remember. Oil rig. Oil means oxidation is loss. Rig means reduction is gain. Okay, so this is a very nice short form. What you know what an oil rig is? Oil rig is something that removes oil from the earth's surface. You can use this oil rig to actually remember what is oxidation, what is reduction. Oxidation is loss of electrons, reduction is gain of electrons. Okay, we have seen the oxidation reduction definitions based on which one can provide hydrogen atoms, which one can accept hydrogen atoms. But this is a very different kind of definition. This is an electrochemical definition of oxidation and reduction. Oxidation is loss, reduction is gain. Oil rig. Okay, now let's see how we can use these definitions in order to understand these reactions. Okay, so what we end up calling the electrode where oxidation is happening, we end up calling that an anode. Okay, so anode is where oxidation takes place, cathode is where reduction. Okay, anode is where oxidation takes place, cathode is where reduction takes place. Okay, let's try to remember this now. Now, there is a very nice trick to remember this also. But for that, I'll need to give you a loan. What this loan means is left oxidizing, anode negative. Okay. On the left hand side, whatever electrode we write, that should be the electrode where oxidation happens. And what is oxidation? Oxidation means it has to be the anode and it will have a negative charge only for galvanic cells. Okay, this is true only for galvanic cells. Okay, so Daniel cell, the way we can write a Daniel cell is zinc is where oxidation happened. So this is a zinc solid rod. Okay, and this is kept in contact with the zinc sulfate solution, which is an aqueous solution. Right, and we write two bars here. These two bars actually represent the salt bridge. Okay, and after that, what two things are in contact with the salt bridge? The salt bridge connects the zinc sulfate solution and the copper sulfate solution. Okay, this is also aqueous, and this is now in contact with the copper rod, which is a solid rod. Okay, now what this lone tells us is the left, the electrode written on the left, negative. The electrode written on the left is negative, which means will have a negative charge here, and you will have a positive charge here. Okay, and this is obvious. It's because zinc was the one who left electrons behind. So on the zinc rod, you will have a surplus of electrons. You will have an excess of electrons, which is what makes the zinc rod negative in charge. Whereas what happens on the copper rod is all the copper ions are clustering there. They are making a crowd very close to the copper rod because they are waiting for the electrons to arrive so that they can settle down. So the copper rod has a lot of copper ions deposited on its surface, which makes the copper rod overall positive charged. Okay, so which is why this is what is called as the cell. This is what is called as the cell representation. The way we represent an electrochemical cell in terms of the anode and cathode, in terms of the oxidation and reduction reactions, is this. Okay, so what you will see is on the left hand side you have anode, on the right hand side you have cathode, and in between you have bridge, okay, meaning the salt bridge. So this is the ABC: anode, bridge, cathode, ABC of the cell, ABC of an electrochemical cell. ABC means anode, bridge, and cathode. All right. So this is how you can remember how to represent a cell, an electrochemical cell, using lone. Lone means left oxidation electrode, left oxidation anode negative. All right. So that would make right reduction cathode and positive. Of course, RRCP doesn't flow out of your mouth as easily as lone, right? So lone is something that you can remember: left oxidation anode negative. Okay. So now let's try to solve a few questions that again have appeared in the CSIR net exam. What is the Daniell cell? Okay. Now what we just saw here is the Daniell cell. Okay, Daniell cell is made up of the zinc and copper electrodes. Okay, zinc and zinc sulfate, copper and copper sulfate connected by a salt bridge. So what is this Daniell cell? Let's look at which of these representations are correct. Now you will notice that they have all written platinum electrodes here. Okay, these platinum electrodes, they are essentially representative of the wires that connect these electrodes to each other. Okay, which means the zinc rod and the copper rod, they are connected to each other by a platinum wire. Okay, so this pen that I'm holding, that is the platinum wire, this is the zinc rod, this is the copper rod, and they are being connected. Okay, so that is what you can see in all of these answer choices. But apart from that, what you have to remember is A, B, C, anode on the left, bridge in between, cathode on the right. Wherever reduction happens, that is the cathode, means you will have reduction here, and wherever oxidation happens, you will have the anode, which is on the left hand side. Now where does oxidation happen? Oxidation happens when zinc gets converted to zinc 2 plus. Reduction happens when copper 2 plus gets converted to copper. Right, so this is ABC. So on the left hand side we should have zinc, which means the third option is not correct and the fourth option is not correct. So these two are definitely not correct. And if you look at the first and the second option, the second option has silver, means the second option is also not correct. Copper one is the correct answer. Okay, the first option will be the Daniell cell, zinc and copper cell. Okay, now how do we know, or why does this electrochemical reaction happen? How do we decide that? All right, so this is based on a concept that we have learned in thermodynamics called as spontaneity. Okay, spontaneity means that a reaction can happen, or a reaction is spontaneous. Spontaneous means automatically happens of its own. Nothing else has to be there in place for the reaction to happen. For example, if you take HCl and NaOH and mix them, the reaction happens on its own. You don't have to actually do something to HCl and NaOH to actually make them react to each other. You just have to mix them and the reaction happens on its own. That's a spontaneous reaction. All right. And what does spontaneity depend upon? Spontaneity depends upon Gibbs free energy, or change in Gibbs free energy. Okay, delta G is Gibbs free energy. All right. And how does it depend upon delta G? The way it depends upon delta G is that Just erase this part. Right. The way it depends upon delta G is if the value of delta G is negative, okay, delta G naught is less than 0, then the reaction is spontaneous. And if delta G naught is greater than 0, the reaction is non-spontaneous. Whereas if delta G is equal to 0, the reaction is in equilibrium, which means it will be a dead cell. Okay, there is no current flowing through it, so there is no cell, there is no electric potential difference. Okay, now if delta G naught is less than 0, okay, if you look at this formula, delta G naught is less than 0, which means this E naught is the standard cell potential. Okay, this is the standard cell potential. This E naught and delta G must have opposite signs because you have a negative sign here. Okay, you have a negative sign there. So delta G naught is negative of naught. All right. So if delta G naught is negative, it means E naught must be positive. If delta G naught is positive, it means E naught is negative, right? Which means reaction will be spontaneous if E naught is greater than 0. And this E naught is essentially, E naught is the reduction potential. Not as a reduction potential, which means it tells us the possibility of reduction happening. So if E naught is positive, it means reduction is spontaneous. Reduction will happen automatically. If E naught is negative, it means oxidation is spontaneous. Oxidation will happen spontaneously. All right. So that is what we are seeing here. Higher E naught value means there is a more spontaneous reduction. Lower E naught value means there is a more spontaneous oxidation that will happen. Okay, so this is again the numerical aspect or a numerical notation for electrochemical reactions. Okay, based on the value of E naught, whether E naught is positive or whether E naught is negative, you will find that reduction happens or oxidation happens effectively. Okay. So let's again see a question based on this that appeared in the CSIR net. This was a question from June 2014 exam. All right. So what has been given to us in this particular question is there are three reactions. FeOH twice is converted to Fe. All right. Which means this will be an Fe2 plus ion. This will be an Fe2 plus ion. But because FeOH twice is not soluble, FeOH twice won't dissociate to give Fe2 plus. But Fe2 plus or the iron with +2 oxidation state is getting converted to iron solid, which is 0 oxidation state. So that is reduction that is happening, and its reduction potential is given -0.877. Similarly, for reduction of aluminium, the reduction potential is given aluminium 3 plus, and for the reduction of silver plus AgBr will have Ag plus. For Ag plus to convert to Ag solid, the reduction potential is again given here. Okay. Now, what we have to figure out is the overall reaction for the cells in the direction of spontaneous change will be. So, which reaction will be more spontaneous, which reaction will be less spontaneous. All right, that's what we have to figure out. Now, what we have seen is whichever one has higher E naught. So, what we have seen is high E naught means reduction. Okay, so the highest E naught is what? 0. So this AgBr has the highest reduction potential. After that, you will have FeOH twice -0.877 and then aluminium. So Ag plus greater than Fe2 plus greater than aluminium P plus in terms of reduction potential. So whichever one is the higher one, that will get reduced. Now look at the first one. The first one says cell A and B. A and B means you have Fe and Al3 plus. A and B, so if you have Fe and Al3 plus, Fe will be reduced. This is correct. Okay, Fe does get reduced. A and C also Fe is reduced. So if you have A, which is Fe2 plus, and C, which is Ag plus. So in Fe2 plus Ag plus, Fe won't be reduced. What you will get is Ag plus is reduced. Means the first option is incorrect. Okay, look at the second one. Again, A and B, Fe is reduced. That is correct. A and C, Fe is oxidized. Yes, that is also correct. in A and C, you have Fe2 plus with the lower reduction potential, so that will get oxidized, and the other one, which is silver, sorry, yeah, silver plus, that will get reduced. Means the second option is correct. In the third option, again, you have Fe oxidized here, which means this is wrong, so this is correct. Overall, the third option is wrong. The fourth option, cell with A and B, Fe is oxidized, that has to be incorrect. Fe is reduced, that is also incorrect. Fe oxidized in this case, right? So second option is going to be the correct answer. Okay, so what you have to do is you have to look at reduction potentials to figure out which reduction potential is higher. So what we found was silver has the highest reduction potential, Fe has the second highest, aluminium has the third highest, and based on that we can solve this. So both statements are correct for the second option, so second option is the correct answer here. Okay, let's solve one more question. Fuel cells provide clean electrical energy to a variety of applications, include automobiles, stationary power sources, normal hydrogen combines with oxygen, and by this reaction, in fact, you get potential generated. Okay, so what we know is 26 electrons are exchanged. Okay, what we know is 26 electrons are exchanged, whereas the free energy delta G naught is given. Delta G naught is 2746.06 kilojoules per mole. What we have to find is its open circuit voltage, okay, which means we have to find the value of E naught. All right, now, we have seen a formula for this earlier. Delta G is minus NF E naught, right? So delta G is minus NF E naught. We are going to use this formula. So E naught is equal to delta G upon minus F, and we simply have to substitute values here and solve. So delta G naught is how much? 2746, but this is in kilojoules. Make sure that you convert it to joules, which is your standard unit, SI unit, into 10 raised to 3. All right, here. So this is 2746 into 10 raised to 3 divided by, now n is given to be 26. Okay, 26 electrons were exchanged. That is what is given to us earlier. Okay, so here what you see is n is 26, and that is what we will substitute here with a negative sign though. Minus 26 multiplied by 9 multiplied by the value of F. F is 96,500 coulombs, which can approximately be written as 10 raised to 5 coulombs. Because we are not allowed a calculator on the CSIR net exam, approximations are the way to go. So if you write 10 raised to 5 here, this now you can approximate. So this 26 will get cancelled with 2700, approximately giving 100 here. Okay, and this 10 raised to 3 and 10 raised to 5 gets cancelled, giving 10 raised to 2 here. The answer is going to be approximately 1 volt, and the one that is closest to 1 volt is the second option. Okay, the answer that is closest to 1 volt is the second option, so that has to be the correct answer. Okay, so just substitute values and solve. We are using delta G naught is equal to minus NF. All right, so that is the correct answer here. Okay, then let's look at one more question. So much more recent question. This is the standard cell potential for the reaction zinc plus copper 2 plus, giving zinc 2 plus plus copper. This is essentially the reaction that is happening in the Daniel cell, and the cell potential is given. E naught value is given 1.1. All right, and what we have to calculate is the Gibbs free energy change. Right, so again, same formula, delta G naught is equal to minus NF naught. All right, so just substitute. Now, how many electrons are being exchanged here? Zinc becomes zinc 2 plus, means the number of electrons exchanged are 2. Okay, and copper 2 plus accepts 2 electrons. So again, 2 electrons are being exchanged. This will be minus 2 into F, we said was almost 10 raised to 5 approximately. And then we can write 1.10 volts here. This is close to 2.2 into 10 raised to 5, but this answer will be in joules per mole. Okay, because everything that we have used is in SI units. If you convert this to your kilojoules per mole, because if you look at all of the answer choices, will have kilojoules here. Okay, whereas this one has joules, but it's just minus 212. Okay, whereas the answer is 2.2 into 10 raised to 5. All right, so this is definitely incorrect. If you convert this, what you will get is 220 into 10 raised to 3 kilojoules per mole, and the one closest to that is the second option. So the second option has to be the correct answer here. Okay, let's look at the next question. This is the last question that we are going to try in this particular session. The standard free energy of the reaction AgBr giving Ag plus Br minus aqueous is closest to 1. Okay, now the free energy, to calculate the free energy, delta G naught is equal to minus NF E naught, and this E naught value is something that we need to calculate. All right, now how do we go about doing that? If you look at this first E naught value that we have been given, AgBr giving Ag and Br minus. So here what is happening is AgBr getting converted. It is essentially accepting an electron and getting converted to Ag solid plus Br minus. So the Br minus in bromide, in silver bromide, whatever Br minus was there, the same Br minus is staying here. So there's no change there. But you had a silver plus here. You had Ag plus Br minus. You had a silver plus, which gets converted to silver solid, which has the charge, so which is electrically neutral. So there is reduction happening here. Okay. And the second reaction is where Ag gets converted to Ag plus. Okay. So what will happen there? Ag solid will get converted to Ag plus, okay, which is an aqueous solution again, and it will lose an electron. That is an oxidation that is happening. Okay, so here what you're getting is oxidation, right? And because these potentials that are given are always reduction potentials, here the E naught value will now become negative as 0.80 volts. That is because this reaction is an oxidation reaction. So we have to change the direction of the reaction. We have to invert the reaction. This is why the reduction potential becomes negative of what it was. 0.80 was the reduction potential. It will become positive, and minus 0.80 will be the answer. Okay. So now the overall reduction potential will be, or the E naught cell, this will be 0.07, which is for silver getting reduced to Ag, okay, silver plus getting reduced to silver ion, and in the next reaction, silver plus ion, the solid silver, the silver atom is now getting again oxidized to silver ion, so it will be minus 0.80 volts, which gives you minus 0.73 volts. And then if you substitute delta G is equal to minus NF E naught, N obviously will be 1 because there is only a single electron that is being exchanged, both cases, all right, will be minus of 1 into 10 raised to 5 multiplied by E naught value is minus 0.73. And if you actually multiply this, your answer will be 0.73 into 10 raised to 5, or 73 kilojoules per mole approximately. So the one closest to that is the third option, 70 kilojoules per mole. Okay, so this is how you can solve these questions. Calculate the standard cell potential and then convert it to delta G. All right, so this answer is obviously what you get is in joules per mole converted to kilojoules per mole to get the final answer. All right, so these were some of the questions that have appeared in the CSIR net exams based on galvanic cells. All right, so if you want to continue watching such lectures, make sure that you subscribe to our channel. Our channel is IFAS Chemistry. subscribe to our channel. There is a subscribe button right here below. Subscribe and click the bell icon next to it so that you get notified of every new lecture that we are posting your way. Okay, so we are going to start a brand new course for CSIR net in English only, and make sure that you register for this course as early as possible. 14th of June is the batch start date. Okay, so before 14th of June, go to our website or call our number and register for this course as early as possible. Obviously, don't forget to subscribe, as I've already told you. And if you have liked this lecture, make sure that you hit the like button that is there below, so that we know that you appreciate our efforts in this particular video, in these particular courses that we are creating for you. And make sure that you share this video with as many of your friends as possible, especially friends who are interested in attending the entire CSR net chemical science course in English. Okay, thank you for paying attention and happy learning. Until our next class, goodbye from me.